What are surface codes in fault-tolerant quantum computing? Imagine trying to keep a delicate glass sculpture safe from every bump and shake. In quantum computing, that's what error correction aims to do for quantum information. Surface codes are one of the most promising ways to do this. They help protect quantum data from errors that happen during calculations. Fault-tolerant quantum computing depends on these codes to work reliably. Surface codes are a type of quantum error correction that uses a two-dimensional grid of physical qubits. These qubits are tiny units of quantum information. The grid looks like a chessboard, with each square holding a physical qubit. The main idea is to encode one logical qubit, which is the ideal, error-free quantum bit, into many physical qubits. This makes the logical qubit much more resistant to errors than any single physical qubit. In surface codes, there are two kinds of qubits. Data qubits hold the actual quantum information. Measurement or ancilla qubits are used to check for errors without disturbing the data. These measurement qubits perform repeated stabilizer measurements. They look for errors like bit flips, where a 0 becomes a 1, or phase flips, which change the quantum phase. The results of these checks are processed by classical algorithms that identify where errors occurred. Once errors are found, they can be corrected, keeping the logical qubit intact. One of the biggest advantages of surface codes is their high error threshold. This means they can handle a relatively high rate of physical qubit errors before the logical data becomes unreliable. This makes surface codes practical for real quantum hardware, especially since they only need local interactions between neighboring qubits. This fits well with many current quantum platforms that have limited connectivity. Surface codes are inspired by ideas from topological physics, involving objects called anyons. This topological aspect makes the codes especially robust against local errors. To manipulate logical qubits encoded in surface codes, quantum gates are performed by braiding or moving defects in the grid. This process is called braiding and allows for fault-tolerant operations like the Hadamard, phase, and controlled NOT gates. In real-world experiments, researchers like Google have demonstrated surface codes that achieve error rates below the threshold. Increasing the size of the code grid reduces logical errors further. Although surface codes requiring many physical qubits for each logical qubit, their ability to correct errors and work with two-dimensional layouts makes them the leading approach in building scalable, fault-tolerant quantum computers. Overall, surface codes are a key piece of the puzzle in making quantum computers reliable and practical. They help turn fragile quantum bits into sturdy building blocks for future technology.